Hello, gentle readers. It's February 3rd, 2024, and it's Saturday. It's kind of sunny and nice out for February. It's really sort of warm for February historically, though with the way things are. There's what's called this global warming, which is really, it's kind of upturned the heat as with regards to traditional estimates of the temperature. So that's kind of what's ongoing. And then what today I hope to do is to talk some more about moment and motion. And that the idea is that I've had some time to review some of the talks in the descriptive differential dynamics. And it's kind of help to digest that a little bit more, because it was just kind of extemporized at the time to consider these notions of the deconstructive accounts of arithmetic and algebra, and how you can look at arithmetic in one of two ways at least. One is you increment and multiply, add and multiply, and then they're inverses and reciprocals, and so you end up with long division at the end, and those being the four operations of arithmetic. And another way is to look at it for any kind of magnitude. You can either increment it or divide it. So you have two operations, and then they work in as either way how they build the modular in the middle. So one way to think about that is that the usual conception and notion of the set theoretic descriptive set theories account of a model of integers is a sort of lacking some context about that. It's not just the elements that comprise a space, it's a space that contains the elements. That there's necessarily this complementary dual and distinction to establish deductively and fully, so that overall there's a consistent middle in the milieu of then that it's still indeed so that the usual arithmetic operations and notions of trichotomy, that which is greater or less than or equal, and the transitivity of that relation, and equalities and inequalities and the transitivities of those relations, then make also for that the implementation of the model of the arithmetic can, according to this sort of deconstructive and reconstructive account, result of fuller sort of dialectic about that. So getting into that, then there is, of course, that there's the usual general notions of we're provided with the Cartesian coordinate setting, and we usually think of that as the orthonormal in the xy plane, and the coordinates result at the ordinates, or where the vertical and horizontal lines respectively connected to a point drop to the axes. And so then there's the notion also of the polar, that another way to do that is that there's the ordinate, as it were, just reaches from the point and points at the origin, and then that's associated with a distance and an angle. So this is the Cartesian plane, and the usual notion of the coordinate setting. And so this idea of the identity dimension is to say, well, what happens is that it sort of results that the magnitude of the dimension or the ray of these values, just having an axis at all, or just a ray, really makes the dimension, the die meaning two, and mention as of the mensuration and measurement, that is sort of results that this identity dimension is a pretty great idée fixe. And then as with regards to all such manners, the usual development of the integral analysis and the linear fractional equation and Clairaut and D'Alembert, and getting all up until we get up to like Rodriguez formula and stuff like that, really has that it's pretty great that the setting of that makes for less, starting with less than, a full piece of paper that's infinite in every direction, vis-a-vis saying, well, we just kind of start with this course, measuring it out in the quadrant, and then be able to build it in the octants, and as those unfold, that it sort of results in a nice way to consider and look at these things. And that it's on paper the same way, and that graphically it's the same way. That's made me happy, and there's still quite a bit to be developed about it. Another thing that was a concept out of that was the right hand, left hand, complex coordinate setting, where instead of having to start with a full plane already and then fill it out with the Argand plane or Wessel plane, the complex numbers, and the usual result that there's only one field isomorphic to the reals, including this complex number plane for all such manners of analyticity about the Eulerian and Gaussian analysis of the complex numbers, that it was read off a very neat branching from when the complex numbers are defined and it's given the writing of what their operations entail, and then with regards to the definition of division of complex numbers, that then it results that you can establish one way and the other way this idea about how to again make for these inner and outer products that don't really necessarily so exist, or they would be indistinguishable, indiscernible in the usual outer product setting of the plane, which is, after all, the closure of the algebras, these groups or fields or elements, that instead these sort of semi-groups make for this semi-dimensional setting where the identity dimension helps affect a reflection for a given parameter that it's changes in terms of the ratio, makes for a pretty cool and great little milieu and a setting. And so I appreciated that, and I'm beginning to appreciate that. And it's this is just what I've studied a little bit since the previous talk and thinking about these talks. So then another idea that arose from that is the identity dimension, the complex analysis, and then the usual notions of the singularity and multiplicity, and that just kind of goes back to this whole notion of the spiral space filling curve, which results the same thing, which is in infinitely many dimensions. That once it just goes out, it fills this space, again for this notion that the geometry makes is geometry a point in space instead of points, lines, planes, ... Because we have this whole notion of these surfaces and their content as of a volume, an area, or a space of these things. That I feel pretty lucky to have found those, because they really help to fulfill the requirements and desiderata of a theory of universal mathematical objects that implements geometry. Well, I found a couple of books, and I thought to look at them, because we've been talking about waves and moment and motion, geometry is motion, waves in their media, and the notion of the wave as a pretty usual formalism, and a very apt model of energy in its state of motion, or as it comes to rest in any sort of setting, that it's amorphous. Everything that can be just kind of considered then to be of these waves. That one thing, and I haven't really got into it very much, is the wavelet. So what is the wavelet? The wavelet is basically the idea of what starts a wave. And so it's really kind of associated with this whole idea of the linear impulse and this whole theory of some potentials, as about that the wavelet can be considered kind of like, we think of it, we call it the kernel, Kernel, the kernel, or the generator sometimes of these things. And then the idea of that, kind of like waves have their constructive and deconstructive interference, you can add the mathematical functions that are waves, and they make mathematical functions as of waves. Then it's similar that the ideas of the wavelet is basically a deconstructive account of the basis of the waves. And so the study of the wavelets and wavelet mechanics and wavelet analysis, it has a lot going on. And so when we talk here about the Fourier style analysis as the usual way that periodic functions, sinusoidal functions, orthogonal functions, sine and cosine are usually used as elements that can make for an effect of the transforms in a domain vis-a-vis usually frequency and time. Then it's as well that the wavelets have their own sort of world about that with regards to the radial basis function and wavelets, and that there are many different ways, or at least a few, and I found one or two that can make it that a wave has is of wavelets has that the wavelet mother is kind of the progenitor of these things. They come from this mother, the wavelet mother, that there's more than one formulaic approach to define the mother of all wavelets. In this matter, is sort of an elementary or rudimentary or fundamental sort of mathematical object. So I haven't. I just kind of I'm speaking to the wavelet as just kind of an aside, because I was just reminded of that as early as speaking about it. Because what I got here is some books, and one of them is about medical imaging, and so I'm not sure if they actually mention that in this book, but it's something that would be appropriate these days, because a lot of what is the use of sensors and devices to affect the realization of, after remote sensing or imaging of usual optical light, then it also gets in here into X-rays. And so this book, Introduction to the Mathematics of Medical Imaging by Charles L. Epstein, Dr. Epstein, Introduction to the Mathematics of Medical Imaging is a great mathematical textbook at the graduate level of sorts, and it's from Pearson Prentice Hall from the Department of Mathematics of University of Pennsylvania. And what it has is a description of the models of X-rays, and for a note on usage is to follow that briefly. And it helps describe then what are the theories of the mathematics behind, and here we talked about the light lake, and with regards to diffraction and reflection and refraction and diffraction and refringence and these such matters that occur as the optical effects in the light lake, that the geometric is considered the linear, and the optical is considered how it all focuses around, that focus rolls over the focus, and this usual notion of the linear, kind of like right-hand rule, left-hand rule, which way is up, optical over the focus, sort of convention, or it's kind of explaining orientation in light. That this book is really, it's just great because it has a didactic approach and introduces pretty much all the definitions you need to get an understanding of the mathematical models, given their reasonable preliminaries and the prerequisites of a curriculum in mathematics, and it's quite standard. And then also it helps explain the attachment to the physical models of the effects of the X-ray, Roentgens, or the radionuclear, in terms of here that there's a usual distinction in the light, like in radioelectric and radionuclear and optical as different empirically, vis-a-vis that they have this, that some of their behavior is modeled all the same, is the transported energy, and as was discussed a little bit earlier, in helping to disambiguate these empirical settings from variously how they have it, so that they have a reconstructive account that has them sort of in the same quantities, that they're different quantities. That the author helps explain, like, what is the power of an X-ray, and the note on usage is as with regards to attenuation. So when I say attenuation, I have attenuation and dissipation, or that dissipation and attenuation are a tendency and a propensity. And so with regards to one doing work and the other not doing work, and this is that what rises must fall, the fundamental law of least action vis-a-vis the inverse, and those being these fundamental sort of axioms, that then attenuation is, as in transmission through a media, in terms of the intensity of the ray, it's the rate at which the intensity of the ray decreases. So it's in this setting, it's as for the flux, it's as of this sort of quantity vis-a-vis that it's well defined, and it's to be kept that it's the same word throughout all of physics. Attenuation and dissipation here, and oscillation and restitution here are the exact same words through all of physics, all the models of mathematical models and physical models. Similarly with flow and flux, those having a distinction and a contradistinction for this liquid model and then the light-like model, or the in terms of states and matter, the slow and the fast, or the near and the far, for this near field, far field stuff, and the effects. So that's just to note that then in this particular case, that's just an example that as a descriptive property, attenuation, that then it's within this wider milieu of all the fundamental and elementarily indiscernible things, that then there's open and closed systems, and open and closed systems, and open and closed systems again. Any system, or here a wave in time, all parameterized by time in the configuration space, according to the configuration and energy of this experiment, or this ansatz, this setup. That anyways, this is a pretty great book. So the chapters of this book are measurements and modeling, introducing dimensional analysis, and he talks about finitely and infinitely many degrees of freedom, this being with regards to what can be considered fixed and what would be considered not fixed or free, and with regards to those things. Linear models and linear equations. So here he helps explain some of the great utility of linear algebra, and talking about solving linear equations, and brings in complex numbers and vector spaces, and this was, here it's just called the Eulerian Gaussian sort of analysis, and its great facility and utility. And then he talks about a basic model for tomography. So tomography is like, if an atom is uncuttable, then tomography is making slices. So this is like the X-ray imaging. There's a bunch of different technologies that are used these days that basically affect the reflection that various forms of rays in the electromagnetic and in the radionuclear, and if not so much light per se, will go through a medium that's otherwise opaque, and then with regards to its what either is transmitted through it or is with regards to what's reflected off it is one thing. And then there's also the nuclear magnetic resonance imaging, which has its own sort of explanatory reasoning and as to why it is so. And then this tomography is basically establishing voxels. If voxels of volume elements were pictures or picture elements, that when you think of a picture as just its graph of its chart of its lattice of elements, and each one having on or off for a grayscale image or monochrome, and then in volume and space just filling those up, then is basically that's what tomography is making a chart or this graphs in each of these slices. So he explains that there's a very well-known empirical law called Beer's law for X-ray tomography, and this is basically how much different materials like flesh and bone have as factors their coefficients that affect that for a given intensity of X-ray radiation or Roentgens, that the attenuation is so, and so that then it's kind of possible to identify different materials by measuring how much it's different on one side or the other. He goes to a bit of a careful explanation also to detail that while there's an effect that there's an optical effect in the rays that according to when the intensity is not high enough that there's this randomness. It's basically the effect is a stochastic model of what falls out. But at the same time, increasing the intensity enough to get more and more precise results damaging ionizing radiation, and that there are limits to the health of what the configuration and energy of this kind of experiment could be, because it's always interference. And so anything that's sufficiently strong to get the closest approximation would also be sufficiently strong to cause here what's damage. It is with regards to X-rays, millimeter wave radar, the electromagnetic, otherwise about the radionuclear, any of these kinds of things. And then he talks about a point source device, some physical considerations, definition of the radon transforms, or radon. So you got Nicodemus radon. And so we talk about Fourier style and the Fourier transform, Nicodemus radon, and their transform. You got Z transform, Mellin transform, Hankel transform. Each one of these is built up as a different sort of the orthonormal basis functions that allow it to be treated up as separable. So you get out two different components in the component analysis. So there are tons of kinds of transforms, and there are great uses with regards to the convolution, the convolutional setting, which makes it so that in given particular domains of analysis, that it works out that then each one of these they're mostly built up with the same sort of setup as the Fourier style analysis, with regards to their properties. That any pair of functions that's orthogonal according to Fourier style analysis can be used to implement a transform in its own sort of analysis given some of these other properties. And so that's just something that it goes into an example in this setting that it's one of the most well-known and usual approaches to then implementing in machines, computers, according to these sensors and their measurements, and the mathematical model of these physical models of the theory of the things, then it sort of results that then there's also getting into what were these wavelets. So there's basically these notions of the transforms based upon orthogonal functions, and then there's wavelets. And so then they both have, in terms of the operator calculus, that they affect being these sorts of transforms for convolutional operators, which is then, it helps explain that mostly then these things get pulled apart in terms of frequency and time, and then to help show over time what is a snapshot of something. Whereas otherwise you think of a snapshot of something as just like at a time. Then this frequency transforms help to kind of break that apart and show a picture of an object in a wider setting. So this is key also in these other kinds of notions, because in moment in motion, then there's the ideas of kind of like what is this windowing and boxing that helps show an event when it's not just an instantaneous event, to establish this analytical character, because then these things can just be kind of added back together or treated as quantities. So there's lots to be said for analytical methods involving the transforms and the convolutional, and with regards to quantities, and with regards to applications. And because many such examples of sensors and meters and measuring devices and remote sensing and spectral analysis, and many other applications or implementations rely on these features, in effect, of the mathematics. And then he talks about the Abel transform, the Volterra equations, and getting into some examples of, in this setting, according to this analysis, like for Fourier style analysis, this Radon style analysis. Then there's these related things that have been discovered, like Volterra's equations, vis-a-vis like Vieta's equations, which are, a different sort of thing. About that, then, it works up for these linear settings that it helps to make some of the things tractable, sensible, and fungible, and tractable. Chapter 4 is Introduction to the Fourier Transform. So it talks about functions with weak derivatives, some refined properties of the Fourier transform. Talks about Heisenberg, the Paley-Wiener theorem, the Fourier transform of generalized functions. So I'll have a comment about that. And he talks about regularity and decay. So here it's attenuation and dissipation and decay as an example of these kinds of things. Radial functions, and with regards to trying to figure out, when something's going to spread out, how do you figure out that it kind of spreads out in a circle, in terms of then, and the circle has no beginning or ending, but then being able to consider that radially, the radial. And he describes some of the limits of this sort of approach, or the failure of localization in higher dimensions. And here that's kind of framed in terms of the nonlinear, or with regards to where partials together don't give an accurate sum, and these kinds of things. Convolution is chapter 5. So basic properties of the convolution product and shift invariant filters, describing the filters, and where a filter is a notion from the signals and the intelligence, information, When I said signals intelligence, I should have said, signal information theory, that the filter is usually then for something like the Kalman filter or other devices that are implemented in the electronic with regards to that then it results that they can perform this sort of analysis. So this gets into the mathematics kind of as what arrives at this as possible. I learned about these things in differential equations courses originally, and I was particularly interested when I learned that any pair of orthogonal functions can make a transform in a family of functions. Then I was like, well, great. Now all I need to do is discover orthogonal functions, and any one of those could be a transform, and it can be worked up. So then when you learn about Henkel and Z and Mellin and Fourier and then off into these wavelets and these kinds of things, that these days it's a lot easier to find a lot of these different approaches. And just like you can find lots of different distributions in probability theory, vis-a-vis the bell curve or the exponential power law. Vis-a-vis here, for example, the Fourier transform and stuff like the cosine transform and wavelet transforms and these kinds of things. There are many more well-known things, and they put them all in great tables and then show interesting attributes and characteristics of them with regards to their suitability for the grab bag toolkit of methods, and then as with regards to their related terms, and usually with regards then to the numerical methods which can be applied and the error terms of those, because then eventually that just gets tossed to a computer to crank out some numbers, or implemented in electronics to put out a signal, and with regards to trying to figure out how that is a useful thing. So he talks about the delta function, of course, that's used everywhere in convolution and filters. Dirac's delta, the infinite spike at zero with infinitesimal width, with area 1, exactly. the Radon transform. In chapter 7 is the introduction to the Fourier series. So he kind of builds up this approach of showing what the Fourier transform is first, and then its properties under operator calculus, and then gets into the Radon transform, about the central slice theorem, the Radon inversion formula, filtered back projection, the inversions, and the Hilbert transform in terms of your functions with bounded support, and about the regions of analysis where it's well defined, like we say Hadamard says it's well defined in this kind of case, and what those kinds of things are. The Hilbert transform, the higher dimensional. And then he gets into Fourier series and decay of Fourier coefficients. So here's helping describe that when you have this this transform is going to indicate a difference in time series data. And so when you evaluate the Fourier style coefficients, then he's able to apply some implicits or scaling to them as quantities that make them these implicit quantities, implicit and explicit quantities. So this is something to help just explain a little bit on the surface what it means to do, then is with regards to getting into this 500-page book and working through all the formulas and analysis with regards to then being able to print that out and be able to implement that in electronics and end up with, you know, a medical scanner, or what you might want to consider it maybe. The application. So then it gets into general periodic functions, convolution and partial sums, and the Dirichlet kernel. Now the Dirichlet kernel and the Fejer kernel were key things when reading from the Fourier style analysis with regards to the book that is still underway here, being read, about the heat equation and the Fourier style analysis. So this of course is a very usual and common regular formalism that everyone's expected to understand. And then he gets into the Gibbs phenomenon. Here there was discussed hysteresis and ringing, and the interesting analytic behavior at the edges of the bounding box, or the windowing and boxing, which results this region of analysis for the Fourier style analysis. And so this helps to remind them. And then he mentions Fejer means. So he kind of instead of having kind of like Fejer first and then Dirichlet and then defining what it's about, it's kind of built up a different way a little bit about this L squared theory. So when you talk about L theory, whenever I see L for L theory, I think Lyapunov, and it's a application up above in the operator calculus, and I'll need to study that a little bit because I'm not quite sure what it means, but it has with regards here that it's introduced that it's with regards to Dirichlet and the existence of derivatives and their continuous in nature and their discontinuities, and with regards to a lot of the stuff that we read in descriptive differential dynamics about the Fourier style analysis and its limits. And then chapter 8 here is sampling. So sampling is a great and important thing to consider with regards to the sampling, measurement, and observer effects, or the observer, sampling, and measurement effects. And that's as to where any type of there's the passive sampling and active sampling in a sense. And so it's kind of well understood that when there's anything that's active sampling, basically is in some sense an interference of things, like the radar and sonar, as we're talked about here, or this X-ray tomography, or these kinds of things. And so this sampling, observation, and measurement is the idea to have these kind of three descriptive terms so far. And what they reflect is what results a sample, or that also a sample as what is the perceived value of an event in the sample space, the support space of the probabilistic universe of the world of possible events, and which one it is. It has that the sampling is basically tallying one event, and then measurement is quantifying that event, and then observation is that events are a continuous stream of events in time series data, all parameterized by time. So this is then the idea that different reflections on these, and by reflections I mean contemplations, vis-a-vis their reflections in terms of symmetries and reflections and refractions and diffractions and refringens, has that these sampling, observer, and measurement effects are kind of key notions. And here, this chapter is about sampling from a continuous domain and deriving a value in the discrete domain. And so when you have sampling, then in the signals information, what you should know about is that there's Claude Shannon and then there's Nyquist. And for both of whom kind of independently developed this notion of sampling theory. And so the idea is that if something's at a given frequency, its nature, if you super sample it at least twice that frequency, then in the digital data that results, because you're recording like a value as of a wave or as of a flux or of a flow at a surface of things, as digital values like waveform audio, meaning we'll have for a given range of frequencies the intensity or amplitude at each band according to how narrow those can be and how many there have to be. The whole idea of sampling is about the discrete and continuous quite overall, because it is essentially making one from the other, the discrete from the continuous, and then collecting enough of this continuous data to result to say that now it's a representation of this continuous data, and thus we can have this reconstruction of the data according to Shannon and Nyquist, and thus result that then our transforms will operate upon it as if it was from the continuous space of these things, the actual mathematical operation on what's this digital data that's so gathered. So this is the sampling with regards to the analog to digital converter, or the digital to analog converter, also called ADC or DAC or DAC in the design of digital electronics. And he introduces, for example, quantization errors. So this idea that, well, when we quantify or quantize these values, then it's kind of unknown. You know, this Heisenberg introduces himself, and and then when we call that normalization, so like, well, also, you know, from the whole world of electron physics, let's figure out this sampling, observer, and measurement effect that results discrete quantities, quanta. You know, there's a passing note is like, in theory, you know that there's a theory under this that's kind of relevant. So then chapter 9 is filters. And so filters, he defines some filters here. Causal filters, the bandpass filters, the inverse filter, after the transfer function, harmonic components. See, this is what I'm going to be reading about. He's got the comb filter and Poisson summation, isotropic, image processing, and linear filter analysis. So the filters have a lot going on with regards to, you know, it's possible to take data, split it out into its transforms, its different components, filter one of those, and then put them back together, because then the filters resulted less information. But then according to putting it back together, it's like you can't tell there's any difference of information. So it's a really key and critical thing in lots of different applications, like image compression or analysis, spectral analysis, lots of different things. And it's implemented in the electronics, and the digital electronics, and it's quite a thing. So and then chapter 10 title is Implementing Shift Invariant Filters. And this goes on for similarly for the radar and the sonar and these other notions, the applications in the technology of remote sensing has that. This describes some of what are the electronic components that go into such devices. And he talks, and an appendix to that is the fast Fourier transform. So when you get into some of these quantization, you quantize the samples, and then some of this stuff runs up in integer arithmetic instead of floating point or real valued arithmetic, and it's fast, the fast. And then they have the inverse, forward and inverse of these transforms, and in regards to the lossy and lossless, these then would become very familiar components of a lexicon of the image compression and the representation of still picture and moving picture image data in time and over time. For example, as one might read, if you want to know how that's applied then in the field, like JPEG, Joint Photographic Experts Group, there's a great book by one of the authors of the JPEG 2000 specification called JPEG 2000. It's called Theory and Practice or something like that. JPEG 2000. That sort of book is kind of like this book, and it helps explain a lot about what a practicing engineer in the implementation of smartphone cameras and these kinds of things knows to carry out these things. Because a lot of time how it works out is that according to the implementation of the file format transfer and encoding, it's really just saying it's like, well, the sensors provide the data exactly in this form raw, and so that's exactly what we use as the input of the algorithm too, and it's and the output or the screen is exactly what is used as the output, and it's according to exactly what it is in the digital electronics. So you want to know these things if you'd like to know how everything works. Conclusion, chapter 10. Chapter 11, reconstruction in X-ray tomography. So he says basic setup, the reconstruction problem, scanner geometries, algorithms for a parallel beam machine, direct Fourier inversion, filtered back projection, linearly interpolated filters, the Shep-Logan analysis of the Ram-Lack filters, sample spacing in a parallel beam machine, filtered back projection in the fan beam case. You don't want to put your hand in the beam case, I'm pretty sure. Fan beam geometry, fan beam filtered back projection, implementing the fan beam algorithm, data collection for a fan beam scanner, rebinning. Some mathematical remarks. Spiral scan computerized tomography, CT. See, in this context, CT is computerized tomography. The gridding method. Well, when you think of gridding or binning, that's really a lot like this sampling. And you basically say, I'm looking at an outline. I lay over some trace paper with a grid on it, and in each grid element, I mark what is the value I can see right under that. When you lift that off, you've got a little gridding of it. You've taken a sample of it. If that's enough, that when you put it back down and write those same values back out, that you can't really tell the picture difference in the picture. That's kind of the idea. .405. So then chapter 12, in imaging artifacts in X-ray tomography, algebraic reconstruction techniques. It's like, well, we got some samples. How do we just kind of make a moire pattern or have it so that the dithering, it makes it so that when you kind of just charcoal that out a little bit and you look at it, then you can't tell the difference. The pointillist, it's from pointillism, is like you make a picture by just having the density of the dots expressing the intensity of the darkness, right? Pointillism. So it's just kind of that writ large for a thing and the way it is. So algebraic reconstruction techniques are just like on the components, so these transform components, figure them out. You got Kashmar's and a Bayesian estimate, probability and random variables. Then he gets into measure theory, random variables, some important random variables, Bernoulli, Poisson, Gaussian, limits of random variables, the central limit theorem, and he says other examples of limiting distributions. So I'll be curious to see that, especially. This is exactly what is, for a long time was like, that's non-standard. And it's like, well, yeah, it's also why the house keeps winning or something like that. They know these things. Applications of probability, modeling a source detector pair, Beer's law. See, this is an empirical law, and then you want to figure out why it is so. And then that it's so in the middle, it's like, well, it's so in the middle just because, like, when you have a wave and you think of it as wave as a motion and the wave over the hump, it's like, does it grow in the middle, or is it always what's coming up and what's going down together? It's two sides added together that make it like so, not just the one thing. So that helps. This is going to help explain a lot for like the identity dimension and its semi dimensions together. These are the kinds of things that help explain how to break down what are otherwise these, their quantities with no interior into those that are so. I find it useful to have pretty simple, fundamental deconstructive accounts of everything, because they are. Random processes. So this is these events in time, sampling, observer, measurement. Then he talks about background material, and he's got an introduction to mathematics and spaces, functions. So function theory and topology after arithmetic and algebra into analysis, basic analysis. So what I wanted to look at briefly is on page 442, he suggests that there are the gridding method. Maybe it's 452. What was that? I need to look again what that was, because I wanted to look at that. The 405, the reconstruction problem, page 405. Okay. We can review the inversion formulae derived earlier, consider how they might be approximated. We write the Fourier inversion in polar coordinates, directly approximating the Fourier inversion formula using the central slice theorem. Leads to the filtered back projection formula. Of course, these formulae are entirely equivalent from the mathematical point of view, absent these implicits and explicits, so they're quantities. So he's like showing how a derivation is like, you can follow this derivation and forget all the rest. When you arrive from here to here, you'll be able to vouch for yourself that you arrive from here to here. However, approximating mathematically equivalent formulae can lead to very different algorithms. So this is that. Then when we figure out how to get it to the algorithms, the number of grid points, about finite element analysis, in order to distinguish the reconstructed values from the actual samples. They're denoted. Reconstructed values at these points are generally non-zero. As remarked previously, real measurements have an interpretation as weighted averages of RF over the cross-section of the X-ray beam. So this is about this flux and flow and the bulk and aggregate of otherwise kind of these particles and these gridded, discrete elements, the elements of the integration of points, the analytical regions, and having been broken down into digital and being put back together, vis-a-vis those being particles, and now they're currents, or rays. In our initial derivations of the reconstruction algorithms, we overlook this point. The effects of finite beam width are easily incorporated. He says, a good reconstruction algorithm is characterized by accuracy, stability, and efficiency. All right. Anyways, this is a great book for helping how to bring together a bunch of different concepts associated with electronics engineering and power electronics engineering and the milieu of the radionuclear about remote sensing with regards to the theory of what can result this kind of stuff. So this is from what's the date here? 2003. So this other book is a great, cool little book. And what it is a dictionary of the history of science. So this was around, this was printed a little bit before the internet, World Wide Web came about. So it's copyright 1981. And so this, in 1981, this would have been, this would have had everything that you would today go find in the wiki about science and its history. So this what they did is they solicited university professors in the history of science throughout largely the United States to write sections. So kind of like the Stanford Encyclopedia of Philosophy is a great webpage, and so on the SCP you can find all these different, kind of, it's a collection of like a dictionary and a little encyclopedia of concepts and some of their sources in philosophy. So this is one for science, and it's kind of like so Professor G.L. Geison, 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 is director of the program in history and philosophy of science at Princeton University. All right. This high-quality work recommends itself to a wide readership. Will focus more sharply than any existing reference work on the history of specifically scientific ideas, and its usefulness will be enhanced by the editor's decision to accomplish their aims in a single volume. So I got this book quite a while ago, and I don't really consult it so very often, but for $8, I thought it was a real great deal. And so what's in it, and with regards to, it's not too terribly used or anything like that, and it doesn't appear to be missing anything. But what I thought to do is look for moment and motion, because moment and motion are kind of the concept of this talk. He says, we have organized it thematically around the key ideas of science. This pleases me. Hence, we have judged it more useful to have articles on the atom, the unconscious, or Mendelism than on Dalton, Freud, or Mendel. So while the developments are, and their names are often associated with the schools of the people, what's important is the field. I'm still reading de Santillana's The Crime of Galileo, and I kind of finished reading it, and this is a good example of like a whole historiography and a setting of what went on and why and what it means today. But here it's just kind of like in 1981, this was the best. So the analytical table of contents, tides, Copernican revolution, double stars, interstellar absorption, Hertzsprung-Russell diagram, motion of the solar system. Well, that says motion. Botany, chemistry, human sciences, historiography and sociology of science, models, the natural philosopher. So science used to be called natural philosophy, and it still is. There are large bodies of application which are mechanized these days. Molecular biology, nature. And you got entry for nature philosophy, which is the same, it's just in a different language. Medicine, mathematics, miscellaneous, philosophy of science, physics. So each one of these sections is only a page or two, or even less, but if some of them are a bit longer and go to several essays, and so then it lists all the authors and kind of the sources of these things. Works of reference useful as guides to further information. General histories of science. All right. It says that Fleu's A Dictionary of Philosophy is the best single-volume reference work on the history of philosophic concepts. I don't know that that's so. Invaluable guide to secondary literature in the biomedical and related sciences. Yeah, right. General histories of science. The scientific imagination. The essential tension. Selected studies in scientific tradition and change. Science in the Middle Ages. Early Greek science. Thales to Aristotle. A history of European thought. Science and civilization in China. An introduction to the history of science. Well, that's, yeah, Sarton's pretty famous. Sarton. A history of science. I really like Motz and Weaver. Motz and Weaver have a history of mathematics and a history of physics. Both of those are pretty good. And they kind of, they're readable. So, moment and motion. Well, we have a few minutes here just to kind of see what it is. Oh, here's infinity. One thing I enjoyed from reading from this was a section on infinity. But we're going to look around for, here's Kepler's laws, and he talks about how he made a derivation of what resulted the ellipse. On the Cartesian interpretation, light is pressure transmitted through vortices of subtle matter comprising most of the universe. On the opposing Newtonian interpretation, light constituted of particles possessing momentum should exert pressure against matter. The solar sail is a device known to work. And as with regards to whether it's flow or flux. Light quantum, light velocity. Magnet, magic, the golden bough, yeah. Let's see also, mass spectroscopy, materia medica, mathematics, melancholia, medicine, mental atomism. Many descriptions of consciousness use the language of mental content, classifying this content into units. Metaphor in science. Mind. Modern logic. We're almost up to moment or motion. Moments. See probability. That's all it says. So in probability theory, we got the moment generating function, which is a way to describe a probability function, distribution with probability functions, cumulative functions, and moment functions. Probability. So what does it say for motion? See absolute space and time, Aristotelian physics, energy, force, mechanics, relativity, viva. That's vis, viva, viva, or vis viva. Motion of the earth, see aberration of light, Copernican revolution. Motion of the solar system. Motivation, See experimental psychology, Gestalt, hypnotism, nature. Motor car, see technology. Movement, biology, see nervous system. Well, this is just pretty great because it's enjoyable to browse around and gain a notion of the context of these thoughts as they are held by many. Mathematics and logic. Gödel's theorem dashed the hopes of logicists and led to set theory being granted a status autonomous from logic. W.V.O. Quine has been influential in this area. Various non-classical logics have been developed, especially in the last 50 years, which have also had impact on mathematics. For example, constructive or intuitionistic logic, fuzzy set theory, and infinitary logics. In addition, computability. Other aspects of logic, such as truth and model theory, also shed light on mathematics. While there is today no definitive view of the relation between mathematics and logic, many aspects of it are being illuminated. Well, all right. I just hope you had a great day today, and thanks for listening along. And what it was is really kind of a talk about the applications of what goes into enough of the analysis to be able to design and implement useful digital analog converters, and then a bit about a history of science. Well, have a great day. I shall so hope it's pretty good.